Hi, everyone. Oh, God, I sound loud, I'm sorry. Ciao, buongiorno, and that is the extent of my Italian. I apologize. Thank you for joining this session today on addressing this transaction challenge in a cloud-native world. Nice to meet you all. My name is Grace Jansen, and if you couldn't tell from my accent, an awful Italian, I am from the UK and I'm not Italian. So I work as a developer advocate at IBM, looking at things all sort of cloud-native Java technologies, so including open source, runtimes, technologies, toolkits, all the way up to sort of deploying on the cloud. So today I want to talk through sort of this challenge of with moving to the cloud and moving to microservices comes great benefits, but also great challenges. And one is data consistency and integrity. And so for this, I'm going to take a look at how we can enable state in microservices using transactions in a cloud-native manner. So the first thing to consider when we look at this is, why are we even bothering to develop our applications and design our applications to be cloud-native? And it's because of this. Now, hopefully you guys have seen Toy Story, otherwise this is completely lost on you. If you haven't, please take that away as homework. Disney is amazing. So we're excited about the cloud. When we think about the cloud, we go, ooh, the cloud. You know, we get excited about all of these behaviors and benefits and characteristics that we can gain from enabling our applications to work effectively in the cloud, whether that be cost optimizations, speed, agility, portability, flexibility, all of these sort of higher level benefits that we can gain. And so in order to achieve these characteristics and get excited, we often take a look at methodologies that sort of lay out step by step how we can achieve becoming cloud native. And one of those methodologies is the 12-factor app methodology. Is very commonly used, and the great thing about this methodology is that it's platform and tool and language agnostic, so it can be applied very widely to most applications. But when we start to take a look at sort of methodologies like this, we start seeing sentences like the ones I've highlighted. It's almost like I had this planned. So you might see it, treat backing services as attached resources, and there's one right at the bottom here, sorry, it's slightly off the screen, that says about executing the app as one or more stateless processes. And that kind of puts into our head these assumptions about, okay, if I want to build microservices or applications that are able to not just barely survive in the cloud, but really thrive in that infrastructure, do I then have to have this assumption, that cloud native has to involve stateless microservices? And this is where I'm questioning it. Is this really the case? Do we have to have stateless microservices like these methodologies sort of tell us, execute it as stateless processes? So I question this idea of, can we be effective cloud-native applications while still having state within our microservices? And so I took a look at a bunch of different cloud-native vendors and organizations, taking a look at what they define as cloud-native to see, do they state it has to be stateless? Ironically there. So taking a look at people like VMware, and again, with any of these, if you want to check them out, I've put the links at the bottom to their references for this. So VMware, people like Microsoft, for example, Red Hat, and obviously people like the CNCF. And actually, when you take a look at their definitions of cloud native, although they mention things like DevOps pipelines, containers, microservices, they actually don't specify that we have to be using stateless microservices. So the first thing I took a look at after looking into all of this was, okay, what do I mean by the difference between stateless and stateful? And in order to define this, I turned back to Disney, because what could be better? So again, hopefully you've seen this movie, Finding Nemo, an excellent movie, I have to say. If you've not seen it, second piece of homework. So in this movie, there is a little fish called Nemo. Nemo gets lost, and Marlin, his dad, the orange fish, goes hunting for him through the ocean, trying to find him and rescue him with the help of a very helpful friend called Dory, the blue fish. Now, these fish are a fantastic sort of character-based way of thinking about stateful and stateless, because we have our friend Marlin here, who is pretty stateful, really. He remembers things really well, and so when he sees events or things happening in front of him, he tends to think about things before he acts. If he sees a jellyfish, he might be thinking about, well, the last time I saw a jellyfish, it stung me, probably best not to go too close. And so he essentially thinks about all of this before acting, so he's not particularly responsive or quick at responding to events happening around him. Dory, on the other hand, is very stateless. For anyone who's not seen the movie, Dory is a very forgetful fish. She has a memory problem. So she literally doesn't have state stored locally. And so when she sees a jellyfish, she acts immediately and goes on, jumps on it because it's great fun. She doesn't think about the consequences or what happened last time or any events that have unfolded in the past, as an example. She just reacts really quickly. So it's a great example of sort of the cons and pros of stateless and stateful. So taking a look now at a little bit more of a technical perspective of what these are. So when it comes to stateless computing, really this is where we don't retain any session information. So the state of the data doesn't get recorded between transactions. What this means when it comes to architecture and scaling is that actually scaling the system tends to be easier, as well as recoverability also being easier. Because if you're recovering, say a microservice goes down, and you need to recover that and reinstantiate it, you don't have to think about reinstantiating the state to where it was before for that particular microservice. So it can be a bit easier to scale and recover. When it comes to stateful, so going back to our friend Marlin, so Marlin does record all the session information. And essentially what that means is we are recording the state of the data at every step across our transactions. So what this means in terms of architecture is the scaling becomes a bit more difficult, and so does recoverability, because we're having to reinstantiate that state. So given all of this, you might be thinking, well, stateless kind of sounds more like what we want in cloud native. Really fast, dynamic, being able to recover from failure inevitably occurs in the cloud. But actually, the reason that we're still looking at building things like stateful microservices is because often when we're building applications, they're mirroring real-life situations that we do within society. And if you take a look at our society, realistically, we don't live in a stateless world. We live in a stateful one. Let's imagine a scenario, for example, where we all forget either our child's or our spouse's or our brother, sister, friends, whatever, their birthday. Now that is not going to go down well. We live in a society where we are expected to have state stored locally. You know, I'm not expecting someone like my boyfriend to go and look in his diary to know when my birthday is. He should probably know that. And so we live in this stateful world where we need to be responding to events given state locally. And so realistically, it can be sort of an assumption that in some applications, not all, but some, we will still need state within our microservices. They can't all be stateless. And so in order to have this state within microservices, often, or within applications, often what we use is transactions. So I came from a biology degree, so you'll notice this in most of my talks. I tend to explain what a concept is before going into it, just to make sure we're all on the same playing field here. So bear with me if you're an expert in transactions already. What are transactions? Essentially what I mean by this is it's a group of read and write operations, and the transaction can only succeed if each of those individual operations are all successful. And so it can either impact a single record or multiple records, and a very common example that's often used is booking a holiday package. So if I want to book a package holiday, I need to have the flight, the accommodation, as well as any car hire or taxis that I might need. If even a single one of those isn't available, my transaction can't go through because I can't get that package holiday. It would just be a flight, for example. And so this is a very common example of where we might need to consistently have state in order to have that overall transaction occur. And traditionally, we might have used something like the ACID model for this. We're in technology, we love acronyms. It was like coming in and speaking Latin when I first joined. So again, I'm going to define each of these just so we make sure we're all on the same page. So the ACID model, what does this really mean and what does it stand for? Well, this is really a guiding set of principles for transactions. And ACID stands for the following words. So we got atomic, consistent, isolated, and durable. What do these mean? Well, atomic is really where we're talking about either all the changes to the data get made or none at all. That is literally one or the other, nothing in between. Consistency, The data has to be in a consistent state both before and after the transaction, isolated, so no other processes can change the data while that transaction is running, and durable, so those changes that you make have to persist. And actually, it's these middle two, consistency and isolation, where we start to see some potential concerns if we were to lift and shift this from a more traditional application into a cloud-native one. And we'll explore that in a bit. And as I said, this is really just a guiding set of principles, and it's intended to guarantee data validity and really support that data integrity. Now, when it comes to utilizing something like ACID transactions, you'll need what's called a consensus protocol. So essentially what that means is if we think back to that definition of transactions and that group of read and write operations, you need to have some consensus about the state of those operations so you can know whether that transaction can be successful or not. And there are lots of different ways you can have this consensus protocol. You can use two-phase commit, 2PC. Again, we love acronyms, so we shorten it. But you can also have things like 3PC, Paxos, Raft. So there's a lot of different types of consensus protocol that you can use just for the sake of simplicity, and also because it's one of the most popular used. In my examples, I use two-phase commit. You look at an example of what would happen if I was to look at applying ACID into a more cloud-native application with microservices. So I'm going to show it in two phases. The first phase is pretty much the same, and the second phase I'm going to show in two scenarios. So in the first phase, again, in this application, I'm using the same scenario of booking a package holiday because it's very easy to conceptualize and understand. So in this, I have my holiday request coming in. I'm using my two-phase commit coordinator in the center there, and that coordinator essentially coordinates each of the individual operations and records the state so that we can know whether essentially that transaction can occur or not based on whether those operations were successful. So that coordinator then coordinates each of the microservices that are involved in this transaction. So in this particular holiday, I'm going to be booking flights, accommodation, and I'm going luxurious. I'm just going to taxi everywhere. So I'm booking taxis as well. So in this, we send the request through to the coordinator, and the coordinator then sends that on to the individual microservices. So now what we have is resource locking. So if you remember back to that acronym, we have isolation. So whilst this transaction is occurring, we can't actually allow any other transaction to edit or try and steal or take the resources within these microservices. So we have to lock that to ensure that isolation. So here we have the resource locking, and this is where we move to, and then we give a response back to say, hey, we either have the resource or not, and that depends on the availability. So this is where we have the various different scenarios as to which response we get back from those microservices. So in scenario one, this is an idealistic world where every resource is available. Fantastic. Scenario two is a less ideal world, but more realistic. And it's where we don't have one of those resources available. And because of the current climate, I chose flights because they seem to be constantly unavailable at the moment. So in scenario one, we have everything ready to go. So we get a prepared message back from our microservices to say, hey, yep, I got the resource you need. I am ready to go with this transaction. So then the two-phase commit coordinator can then send a message back to say, great, everyone's available, so please commit those resources to this transaction. They commit the resources and send a confirmation message back to that central coordinator. That can then confirm it with whatever was used to book that in the first place, whether it's a front end or another back end microservice. And then we can take the money and everybody's happy. You get your holiday, we get our money. Now onto a more realistic scenario where we don't have a resource available. So in this, I've chosen flights. And so although I got a prepared message back from the hotel microservice and taxi microservice, the resource is not available for flights. So this time, because not all of the read-write operations were able to go through, I have to abort the transaction and tell the client essentially that they can't have their package holiday today, unfortunately. Sad times. Now, the issue with this, although it has done what it was meant to do in terms of either going through with the transaction or not going through with the transaction, there are several issues that we need to be thinking about when we're applying this to a cloud-native scenario. The first of those is it's pretty darn slow. When you think about it, you're waiting on a lot of communications with this type of transaction, and you've got resource locking as well. We are essentially having to wait for the slowest service to respond before everything else can be unlocked and the transaction can go through. So if you have a microservice go down, for example, in the middle of that, they're probably going to be the slowest microservice. It might take a while to reinstantiate them and go through with the request. So it is pretty slow. As well as that, you've got issues, for example, like the fact that two-phase commit doesn't work. You can't use it with NoSQL databases. So if you're using MongoDB or something like Kafka, for example, or RabbitMQ, you can't use two-phase commit. So this isn't even available to you. Now, on top of that, we've got things like that are native to cloud native, issues like communication failures. Instead of using a local network, we're now using network communication. And this can, I'm sure you guys are all aware, go wrong a lot of the time. Messages can get lost, and it might be that your microservices has changed location. So if any of these fail, how then do you know, did the microservice receive that message or not? What state are your current microservices in? Is it inconsistent across those microservices? You've also got issues like, what if the microservices that are involved in the operations themselves go down? If they go down, then you're obviously delaying your transaction going through. You've still got resource locking. Maybe perhaps it was halfway through giving that resource and sending a message back. Do you then retry that? How do you know whether that message was successfully sent to the coordinator? So all of these issues start to crop up. And then one of the biggest points of failure within this system is this central potential bottleneck or single point of failure that you have. We're all reliant heavily on that central coordinator. So what happens if that central coordinator microservice goes down? How do you know, have you stored the state elsewhere? Are you able to reinstantiate it? What happens if the microservices have sent a response in the time that it's been down? What happens to that response? Does it just get lost? Do you resend it? So all of these potential issues come into play, and not just that, but because of this resource locking, whilst that central coordinator is down, we're still in the middle of this transaction, and no other transactions or requests can edit the resources that are being used in this transaction. So you're potentially making your application unresponsive to other potential users. So these are all issues that we can have if we were trying to just lift and shift an ACID-style transaction into the cloud. So instead, we might look to other alternative types of transactions, for example, like the Saga pattern. Again, we love acronyms. So what is the Saga pattern? This is really a failure management system. It's designed to be a forward strategy, so we use something called compensating actions instead of rollbacks, and we'll go into that in a bit more detail. It helps to establish consistency, specifically, there's a lot of S's in those words, specifically in distributed applications. So this is really designed in mind with cloud-native architecture. Again, ideally maintaining data consistency and integrity, and it's still using that sequence of local transactions. Now, Saga isn't based on ACID principles. Instead, it's based on something ironically called BASE. I've used that word a lot. The big difference here is, as I've highlighted, the words that I've crossed out. So we love acronyms, but BASE stands for basically available, soft state, and eventual consistency. The biggest differences here are the fact that we've lost this strict consistency and we've lost the isolation. So what this means is that we're now more like an AP system, so we're more aligned to this type of system. If you're familiar with the CAP theorem, you'll be familiar with this concept. If you're not familiar with the CAP theorem, definitely check it out. It's really interesting. It's essentially around how we can't prioritize all three of these factors in our applications, and we have to then select what would be best for our application, whether it's strict consistency or not, or strict availability, etc. So you can have either a CA, CP, or AP system. This one is more aligned with AP because we are giving up that strict consistency. We are now going to be eventually consistent, like that E in BASE. So what does this mean when it comes to our scenario? So in scenario one, we're just going to run through this again, what would happen using Saga instead. Now, there are different ways of essentially managing Saga. You can either have a choreography approach or an orchestration approach, which again, I'll dive into. But in this example, I'm just using a choreography approach just to make it a bit simpler to see and understand. So in this, my holiday requests this time are going directly to the microservices. So we're sending a request into the taxi booking microservice, and that has resources available. So we commit that resource to that transaction. But as you can see, this is now an inconsistent state, because I don't know whether I have availability for my hotel or my flight. It might be that I've given that resource of that taxi to that transaction, and actually the flight isn't available. So I'm going to have to undo that in some capacity in order to be back into my consistent state. So this is where that eventual consistency comes in. So now that I'm sending my second request to my hotel, that's also available, and because it's an ideal scenario, my flight is also available, so it can send a confirmation back, and we can basically say that transaction is finished, all successfully, take the money, and they can have their holiday. Great. What about scenario 2, the more realistic one? So in this scenario, we're all intelligent. I've skipped the first few steps, you get the idea. We've got the taxi, and we've got the hotel. In this case, again, the flight is unavailable. So now what happens is the flight, request it from it, the flight will say, actually, no, I'm really sorry, but I don't have anything for you. So you're going to have to cancel this transaction. So as I mentioned, this is a forward strategy. So instead of rollbacks, what we have is compensating actions. And it's up to you to determine what logic should go into that compensating action. But a lot of the time, it's essentially doing the opposite of what you did in the original action. So in this case, what we're going to do is send that compensating action to say, right, I'm sorry, but I know you reserved that hotel room, but we're going to have to unreserve it. So we unreserve the hotel room, and we unreserve the taxi bookings we've made. And so now we can send a message back saying, really sorry, but we weren't able to get all of the operations as part of this transaction. You can't have your holiday. So as I mentioned, this is the forward strategy. So this is an example here of actions and compensating actions that we might have. The items in blue are the original actions, and the items in yellow are the compensating actions. Again, it's up to you to determine what those compensating actions are, but if we were to book a seat, you probably need to unbook that seat. So generally, they tend to be the opposite. So as I mentioned, there are different approaches that you can take when you are implementing a Saga pattern. The first is choreography, and this is more like the example I just showed. So in this, every single microservice that's part of the transaction essentially publishes an event that is then processed by the next microservice. So in this scenario, there isn't a central coordinator. So there's several advantages to using an approach like this. For example, the fact that you don't have that potential point of single failure because there is no central coordinator. And it's also kind of ideal if you are developing transactions that only use a small number of microservices, because it can be fairly simple to set up and fairly easy to follow. And it's very agile prone. If you are working in an agile team, you're each able to work independently of the other. However, there are also disadvantages with this approach. It's not really suitable if your transaction involves lots of microservices, because it can very quickly become quite complicated to actually manage and maintain. Additionally, sometimes it can be difficult because there's not that single point where you are ensuring that data and the state of each of those operations. And it can sometimes have things like you have a risk of tight coupling here because you're not decentralizing that logic, you're relying on the previous microservice. The second approach is orchestration, and this is what I'm going to use in the demo that I'm going to show. So orchestration is more similar to what we had in that ACID transaction, but still based on the base principles. So in this, we have the Saga coordinator, which acts as that central point with which we can check the persistence of state of the system. And essentially, that's the one that coordinates each of the transactions that are occurring locally within those microservices. Again, there are pros and cons of this. One of the pros is the fact that you have this central point that essentially provides an overview that helps to avoid things like cycles happening among the various different services. You've also got the fact that the business logic is concentrated to a single point. Again, it's also agile prone because you can work independently again as your teams to develop your microservices. And sometimes rollback management can be easier in this approach because you have that central coordinator. Downsides of this one, the single point of failure being quite a big one. There are things that we can mitigate that. For example, by having sort of clusters, so having a master node and worker nodes acting as that central coordinator. And there's a really interesting paper that got published in 2020 on that if you're interested. But also potential failures being, or potential disadvantages, being the fact that you have to have an additional service. So that service is the orchestrator, so you do have to have additional sort of compute power, and the number of interactions that are happening in this is literally doubled because you're having to go back and forth between the microservices and that coordinator, so more network communication going on. So it depends on sort of what your application is, what your transaction is, and how many microservices are involved in that transaction as to which approach might work best for you. So now that we've taken a look at Saga and seen that it can be a bit more sort of in line with our cloud native principles, especially relaxing those ACID constraints, how do we actually go about implementing this in our application? Because at the moment, all we've done is look at high-level topics. So we can use something called MicroProfile. Has anyone come across MicroProfile? Oh, just a few hands. Okay, good. I'm glad I've got an intro slide. Good. Okay, MicroProfile. This is really about, it's an Eclipse project, so it is open source, and it's really designed to help developers who are using Enterprise Java or Jakarta EE to develop applications that are ready for the cloud based on things like microservice architecture. It's a range of different APIs, and it's developed by really a wide range of individuals, including some from vendors, some individuals themselves, just general companies, and they all contribute really to this community-driven specification. So some of the contributors from vendors include all of these companies. So the nice thing about this specification is because there's so much input and contributions from these various different companies, is it can be very easy if you're developing with MicroProfile to use any of them. So it gives you some great flexibility and freedom in terms of what products or tools you're using underneath. And many of these companies produce implementations of MicroProfile. So just remember that if you want to use MicroProfile, it's a specification. So you'll need an implementation to be able to actually make use of it. So these are some of them. Many are open source. The one that I helped to develop is OpenLiberty, as it says on my t-shirt. So that's the one I'm going to show you in the demo slides today. And if you want to find out more about OpenLiberty, we have a website with loads of cool docs and guides, and like you can get interactive with them, and it's great fun. So MicroProfile. So as I mentioned, it's a wide range of different APIs. The bottom sort of pyramid shape that you can see here in my slides, this is the core APIs that come as part of the MicroProfile specification. It's just off the slide, but the latest one out is 5.0. 6.0 is hopefully due out later this year. So in this, you get things that are going to help you with microservices, things like being able to monitor health and metrics when you've got distributed microservices, being able to have external configuration to allow you to deploy your application easily to different environments, things like using JAX-RS, having documentation of your APIs using things like OpenAPI. So lots of really helpful APIs for you to use. And as well as the core stack, there's also this sort of weird L shape that I've made at the top, which is the standalone projects. So these aren't yet part of the MicroProfile stack, but they are developed by the same people, the same community. So the one that we're going to be interested in here is actually LRA. But if you're interested in things like reactive applications or using GraphQL, then check out the other standalone projects. So LRA stands for Long Running Actions. Again, we just love acronyms. And this is essentially what you can make use of in order to utilize something like the Saga pattern. I am on low battery. I don't know why my laptop's not charging. Let's hope it lasts. So MicroProfile LRA, what is it? So it is essentially, again, it's a transaction model, but this is, again, really designed with cloud native in mind. So it's based on the Saga pattern, and it, again, relaxes those constraints of ACID. And it's essentially based on the base principles again. It was really designed to be able to enable this decoupling when we're using transactions in microservices and to help simplify things like error handling and enabling those compensating actions. So the example I have is OpenLiberty and LRA. So this is using MicroProfile LRA and actually using the OpenLiberty implementation. Now, OpenLiberty uses the Narayana implementation of the LRA specification. And essentially, this is more aligned with sort of the orchestration approach that I showed before. So we have two parts to this, the LRA coordinator and the individual LRA participants. And essentially, OpenLiberty then implements MicroProfile LRA using this transaction manager that acts as a coordinator, and it will handle one or more of the participants they could be running on one server or on multiple servers. It depends on how you orchestrate your application. So how do we actually go about using this in our applications? The first thing you'll need to do is enable these features in your server.xml file. So I've got a screenshot here of ours, and you can see that I've got the feature for MicroProfile LRA. The nice thing about both OpenLiberty and MicroProfile is it's more of a plug-and-play approach. So you don't actually have to have all of the features of MicroProfile if you don't need them. The only ones you do need for this are CDI and JAX-RS, which is why we've listed those features here, because they are dependencies for LRA. So you will need those two, but if you don't want to make your application too big, don't feel like you need the rest. So once we've got this in our application, it's really simple to be able to start up an LRA. So all we have to use is two commands, essentially start LRA, create LRA, and then start LRA. I've got a blog actually, which is slightly off this page, but when I share the slides, you'll be able to access that link, and the blog goes through step by step how you can enable this as well. When it comes to actually using MicroProfile LRA, like a lot of the other MicroProfile specifications, it uses annotations. And the three main annotations you'll need, these are like the basic ones, are @LRA, @complete, and @compensate. So @LRA essentially says it's usually at the top end of your class, and it essentially lets you know that it needs to either join or create an LRA method, and it needs to be part of a transaction. The @complete, as the name kind of suggests, is the business logic that happens if that transaction is successful and it's able to be completed. And then the @compensate is what happens for those compensating actions if the transaction isn't able to go ahead and we need to do something about that inconsistent state. So what that looks like is something a little bit like this. So this is all part of the same class, but just to fit it all on one slide, I've kind of cropped different bits of a screenshot and highlighted the annotations that we're using. So you can see here at the top, I'm using the @LRA annotation, and actually I'm using something called LRA.type. There are different types that you can use, so required, mandatory, or I think the other one's requires new, yeah. So in this one, we've got required. So what that basically is, an LRA method is required. If an LRA is already running, we'll just join that one. If there's no LRA running, we need to make one. So that's kind of the middle ground. If you use something like requires new, you will always start a new LRA. If you use something like mandatory, an LRA has to be running. You can't create one. So it really depends on which microservice within your transaction this is as to which type you'll want to use when you're using that annotation. Now, there are other annotations as well. If you want to go beyond those simple three, those are the basic three you'll need to make an LRA participant. But the others include things like @forget, @leave, and @status. These can be helpful, for example, if you have to release any resources, so thinking about those compensating actions. If you no longer want that particular class to be part of your LRA, so let's say, for example, my new holiday, I don't need a taxi, I'm just going to walk everywhere. So I don't need that to be part of my transaction, my LRA anymore. And then we've also got things like @status to report the status of our microservices. So as I mentioned, we do have an app for this which uses MicroProfile and OpenLiberty. So if you want to check it out, it's free on GitHub, and it's using a very similar architecture and sort of example use case. So we've got a holiday booking system, and essentially we've got holiday microservice, flight microservice, and hotel microservice. And this is the business logic in this application is not necessarily what you would use if you were booking a holiday. It's just to show you that logic flow of like how LRA works and how it communicates. So with that in mind, hopefully I have shown you a little bit today of sort of the difference between thinking about transactions in a cloud native world rather than just lifting and shifting the transactions you might have, and the fact that we do still need them in some applications. So stateful microservices are still needed. We do have scenarios where this is still required, and we can't necessarily always just rely on the traditional types of transactions that we might once have. But there are alternatives, for example, like the Saga pattern and open source tools like MicroProfile LRA that can help us to be able to do this. So hopefully it's easy for you guys to at least try it because it is all open source and free. So please do go have a look if you're interested. Things like MicroProfile LRA. As if I haven't set you enough homework already with 2 Disney movies. There's also some actual technical homework as well. So if you're interested in finding out more about this, There's the link that was kind of cut off in the other slides. So that's the link to the blog if you want to look at how, step by step, how to implement it. That's a link to our blog, to our example that is also used in the blog. And then I've also put a link to the MicroProfile LRA spec if you want to take a closer look at those annotations and how to use them. And if you've not come across Saga before, really get a great article at the bottom around Saga and sort of more about what it means and why it's useful. And if you're interested more in the open source projects that I've mentioned, like Open Liberty and MicroProfile, then check out these links. If you've never used them before, both have starter projects, which allows you to get started in literally like 5 minutes. It's a drop down in a web page, and then it gives you a zip file basically ready to go. So that's really helpful if you want to have a go locally trying out these technologies. So with that, hopefully I've given you something to think on, something to consider, and you've learned something today other than Finding Nemo and Toy Story. If you have any questions, I'd be happy to answer them. Otherwise, you can catch me on Twitter at 27.